So we're looking at chapter 7 on the hypothesis testing from this book, first year Edexcel applied maths book. Now you will find that if you're getting stuck on chapter 7, it's often a really good idea to go back first of all and have another look at chapter 6, and particularly this part of chapter 6. Do you understand properly what a random variable is, what a probability distribution is? Once you've understood those ideas and you've understood the idea of what a hypothesis test means, then we need to put those two things together and understand a hypothesis test where we're using the notation and the idea of a random variable, okay, and a probability distribution. Once we've put all that together, then we need to put everything in terms of a binomial distribution. For the first year of this course, it's only really the binomial distribution that we're dealing with. I haven't yet seen any questions where they've done anything cleverer with a hypothesis test other than just ask us for a binomial distribution. They could ask us for things, because we do, strictly speaking, have this discrete uniform distribution, and they could also, if they were feeling mean, they could make up a probability distribution like these ones in this example, and then ask us to do a hypothesis test on the random variable which has a probability distribution that we've sort of been given, or we've had to work out in the first half of the question. If those words random variable and probability distribution there are seeming a bit unfamiliar, if you're not happy with that, if you're not comfortable with me, if you didn't quite understand what I meant by, a probability distribution like this, or a binomial probability distribution, or making up a probability distribution like these ones here, then I really recommend, before you try and solve chapter 7, go back and make sure you understand the things from chapter 6, and particularly section 6.1, which you'll find you can probably answer a lot of the questions on chapter 6 without really thinking back to section 6.1, because a lot of the questions on chapter 6 are asking you about binomial distributions. Actually, the idea of a random variable and a probability distribution, those are the important ideas there. Okay, and there are videos hopefully in the same playlist as this one, so you can just flick back to those if you need to. So that said, hypothesis testing. Now the way we'll deal with this is we'll get the main idea first as to kind of what a hypothesis test is, and then maybe in this video, maybe in the next one, we'll see how long it takes, we will come to this notation, this H0, this H1, this null hypothesis and alternative hypothesis stuff. So first of all, let's put the book aside and just think about what we mean when we're doing a hypothesis test, okay? Now the example that I'll often use for this one is as follows. If you flip a coin 100 times, you would expect to get 50 heads, okay? Let's say it's a fair coin, you flip it 100 times, you expect to get 50 heads. Now it would be possible to get no heads, 1 head, 2 head, 3 heads, and so on. It would be possible to get 100 heads in a row, or 99 heads in a row, or 98 heads in a row, and so on. But you'd expect to get 50. Now that doesn't mean that you'd expect to get exactly 50. It means the expectation of that random variable is 50. So this is a random variable, let's call it x. The outcomes of this random variable are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 10, up to 100. In fact, if you go to chapter 6 and you're thinking quickly today, you've probably spotted that this is actually a binomially distributed random variable with n is 100 and probability of success is 1/2, okay? Now, the outcomes of this random variable are any of the whole numbers from 0 to 100. The expectation of this random variable, the average result, would be 50. But that doesn't mean you're going to get 50 every time. You're going to get 51 quite a bit, you're going to get 49 quite a bit, okay? So just thinking about this, if you've got a fair coin, it would be possible to get 100 heads in a row. But if somebody stood in front of you and said, okay, I've got a coin here, flipped it 100 times and got 100 heads in a row, your conclusion, I hope, would be, I don't believe that's a fair coin. I hope you'd say to yourself, no, I think that is not a fair coin. Now, that's even though you know it is theoretically possible. If you've got a fair coin, you could flip 100 heads in a row. That is theoretically possible. That it's got a probability which is not 0. But the probability is so small that you would be convinced, if that situation happened, you'd be convinced that that coin is not fair, okay? And the same at the other end, if you got no heads and you got 100 tails in a row, you'd be pretty convinced that that's not a fair coin. If you flip the coin and it got 50 heads and 50 tails, I think you'd probably think, well, there's nothing wrong with that. It's a little bit of a coincidence that we got exactly 50-50, but that's fair enough. If you got, say, anything in this area here, 49 to 51, then again you'd be saying that's fine, that's what we'd expect from a coin. So the question is, at what point do you draw the line? If you got 55 heads would you be convinced that that is a biased coin? Is that, you know it could happen, but do you think it's unlikely enough that you're questioning whether this coin is fair or not? If you got 60 heads, if you got 65, where would we draw the line? Now, so far, the only thing we've been able to do, until we understand what a hypothesis test is, the only thing we're able to do is to just say, well, I think about here. I'd say, well, if you get 55 heads, then fair enough, it's probably a fair coin. If you get 56, that's enough to convince me. You just need to sort of arbitrarily draw the line. And the idea of a hypothesis test is to quantify that, is to give us a bit more of a mathematical approach so we can say, right, this is the point where we will be convinced, okay? So let's go back to that idea of if somebody flipped 100 heads, you'd say, well, that's unlikely. I don't think, if this is a fair coin, that's unlikely. It's unlikely you'd flip 100 heads. If somebody flipped, say, 98 heads or more, we might say, well, that's my cutoff. I'm going to be convinced at 98 heads or more, because getting 98 or more, being anywhere in this region, is unlikely, okay? Let's say, for the sake of argument, that your cutoff point was 65 heads, right? I don't know if that's a sensible cutoff point or not, but let's just say you decide that you would be happy that it's a fair coin if somebody flips 64 heads. You would be unhappy that if it's 65 heads. 66, 67, 68, and so on, up to 100, any of these numbers would convince you that that coin is biased, okay? So what you want to be saying is the probability that the random variable x takes a value greater than or equal to 65, that probability is small enough to convince you that it didn't happen by chance. You started off thinking this is a fair coin. You knew that there was a theoretical probability of when you flip this coin, it could get anything between 0 and 100. When you flip the coin 100 times, you got a result in this region, somewhere between 65 and 100, and that was enough for you to be convinced that it didn't happen by chance. Because if it did happen by chance, the probability of it happening by chance, the probability of this random variable, the probability of a fair coin getting 65 or more heads out of 100, that number is small enough to make you think that's unlikely to have happened by chance. That happened because this coin is biased towards heads or something like that, okay? So that's the idea of the hypothesis test. We say, right, if the probability of being in this area, of being bigger than this number, is small enough, then that's enough evidence for me to be sure that, well, not to be sure, but it's enough evidence to me to think that this coin is not fair. The hypothesis that we made in the first place, the assumption we made in the first place that it was a fair coin, I'm now starting to doubt that, okay? Now we've got all the key ideas in there of hypothesis testing, critical regions, null hypotheses, and so on. So let's just start calling things by the technical names then. So this set of numbers here is what we call the critical region. Hopefully you can see that if you're convinced by 65 heads, you'd be convinced by 66 or 67 or 68. So we're not interested in the probability of getting 65 heads. We're not interested in that. We're forgetting that. We're interested in the probability of getting 65 or more heads. Okay. That is our critical region. That's the name we give to that region. So once you've decided, right, this number of heads or more, or let's put things in terms of binomial random variables in general, because that's what's going to happen in the rest of this chapter, excuse me. In terms of binomial random variables, we're going to say, right, if we get more than this number of successful trials, or more than this number of unsuccessful trials, failure trials, then we will be in the critical region and we'll be convinced that our initial assumption was incorrect, okay? So that's the critical region. H0 is the notation rather that we give to our null hypothesis. So the null hypothesis is the thing that we're assuming to start with. So here we started by assuming that this was a fair coin. We started by assuming this was a fair coin and saying we're going to flip it 100 times and see how many heads we get, means that our assumption in statistical speak is that the random variable x, which is the number of heads that we get, is distributed with the binomial distribution with parameters 100 and a half. Okay, so that's our null hypothesis. It gets given that what we are assuming in the first place. H1 is our alternative hypothesis. Okay, so if when we carry out our experiment, the result of the experiment is so improbable that we are in our critical region, then we're going to say, well, we reject H0 and we will accept H1. We're going to say, if we get more than 65 heads, i.e. if we're in the critical region, we're going to doubt that this is a fair coin, i.e. we're going to reject H0, we're going to stop believing the hypothesis that it was a fair coin, and we're going to accept the alternative hypothesis that the coin is not fair, right? That it's biased towards getting heads. Quite an important conceptual point here, not important in terms of getting results in the exam, but very important in terms of understanding what you're doing here with hypothesis tests. Can you see it's not actually possible 100% completely to prove that this coin is not fair? If you flipped it 100 times, you could, by chance, get 100 heads in a row. If that happened, you would doubt that this is a fair coin, but you could never be absolutely sure that it wasn't a fair coin and that something very improbable didn't just happen. Okay, that's possible. In the real world, if somebody did that and they flipped 100 heads in a row, you'd say, well, that's not a fair coin. That's definitely not a fair coin. If they then came to you and said, no, honestly, it really is a fair coin. Look, I don't know what happened. That was very improbable. It really is a fair coin. Will you not believe me? What you would then do is you'd say, well, okay, flip it another 100 times. Let's see. And if they flip it another 100 times and get another 100 heads in a row, you really would stop believing them, wouldn't you? So just because you've done an experiment, let's say we flip this coin 100 times, we've rejected H0, we said we don't believe it's a fair coin, we've accepted H1, we've accepted our alternative hypothesis, we've said yes, we think it is a biased coin. It doesn't mean we can be 100% certain. Just because we've done the significance test, we've got a statistically significant result, we're in the critical region, doesn't mean we can be 100% certain. We need to look at, have we done a good statistical test? Have we done enough trials? Could we do a better statistical test? And this is the essence of the idea in science of having a result which other people can replicate. So if you get a result in your laboratory, can I go away and do it in a different laboratory and maybe even in a different country and get the same result? If we both get the same results, then that means that we've got more evidence towards saying that that result was correct. If something strange happens once, is it going to happen the same way again? Are we going to get the same results every single time? Okay, so this is the whole idea of hypothesis testing is really central to science and the idea of scientific evidence and those sorts of things. So where were we? So we've talked about the null hypothesis and the alternative hypothesis. We've talked about the idea of a critical region. What we haven't talked about yet is a significance level. So this is where we actually quantify this. Instead of saying, well, I reckon 65 heads or more is unbelievable. If you get 65 heads or more, I don't believe it's a fair coin. Instead, we're going to say, right, we'll put a number on it. We said that this event was sufficiently improbable. Well, rather than saying 65 heads or more is sufficiently improbable, whatever that probability is, we do it the other way around. We say, okay, if the region we're in, if the number of trials that were successful or the number of trials that were unsuccessful, that many or more, if we're in that region, if the probability of being in the critical region is 5% or less, then we will reject H0 and accept H1. Okay, that if we use 5%, then that is a 5% significance level test. If we use 10%, it's a 10% significance level test. If we use 20%, it's a 20% significance level test. Now, by this point, if you haven't seen this before, I think these terms and this notation might be getting a bit confusing. One more thing to say, and then we'll do an example and walk you through how these things all fit together. So the thing to say is, think about it like this. If we say, when you get, well, the critical region has a probability of 5%, let's say we're using a 5% significance level, then for us to be convinced that we should reject our assumption, for us to say, I don't think this is a biased coin, something has to happen which has got a 5% chance of happening or not, or less, okay? So the thing that happens has to be so improbable that it only happens 5% of the time, or one time in 20, okay? If you choose let's say 25% significance level, then you're more likely to get a significant result, aren't you? If the critical region, if you find yourself in the critical region, if the thing that happens, that will the event that needs to happen to make you reject H0 happens 25% of the time, then you will be rejecting H0 25% of the time. You're saying my initial assumption was wrong 25% of the time. So you will get more significant results, right? Your results, well, not results which are more significant, but more results which are significant, okay? So your significant result will happen 25% of the time, but it will happen 25% of the time if your initial assumption was correct, okay? So if you choose a big significance level, you've got a good chance of getting a significant result and saying, yes, this is not a biased coin. Sorry, this is a biased coin. We are more likely to get heads. But on the other hand, you're also running the risk of saying it's biased when it's actually not biased. If you choose a small significance level, say 1%, then if you're in your critical region, you can be pretty sure that this is a biased coin, right? You know, getting a result in your critical region with a fair coin only happens one time in 100, so you're pretty certain that this is not a fair coin. But the problem there, of course, is that actually it might not be a fair coin, and you're just not willing to say. You're not going to be convinced enough, okay? So having a low significance level will be the equivalent of saying, well, I'm not going to be convinced that this is a biased coin until I get 70, 80, 90 heads, okay? Having a significance level that would be too high would be saying something like, well, I'll be convinced that it's a biased coin if I get more than, say, 52, 53 heads, okay? You need to pick a sort of good middle ground, and the good middle ground that everybody seems to agree on, which is the sort of standard, is 5%. So a 5% significance level, almost every single question you do will be a 5% significance level, okay? So let's carry on and actually try and have a look at a significance test and how we'd set this out and the sort of questions they ask. Now you'll see here they're talking about one-tailed and two-tailed tests, and we're not going to worry about that too much for the moment. Let's actually just go straight into a question. Oh, sorry, one bit of information I haven't said, a test statistic. So the test statistic, let's read this question. An election candidate believes she's got support of 40% of the residents in a particular town. The researcher wants to do a test at the 5% significance level, whether or not the candidate is overestimating her support. The researcher asks 20 people whether they support the candidate or not. 3 people say that they do. So here the test statistic is 3, or 3 out of 20 if you like. The result that we've got when we've done the experiment, the result that we are saying is, what does this result tell us? Was our assumption correct or not? That is our test statistic, okay? So in the previous example, how many heads did we get when we flipped the coin 100 times? The answer to that question is the test statistic. Write down 2 suitable hypotheses. So the H0 is, we will believe this candidate. We're going to start by assuming that she's got 40% of the residents voting for her. And H1 is that the probability of somebody voting for her is less than 40%, and we'll not worry about why it's less than rather than greater than or not equal to for the moment. We'll just go with less than, and we'd reject the null hypothesis if there are so few people. If we've got few enough people out of 20, that the probability of having that many people or fewer is less than 5%. Okay. And why that many or fewer? Let me just remind you, 3 people out of 20. If you say, well, 3 people out of 20 would convince me, then 2 people out of 20 would convince you, 1 person out of 20, and 0 people out of 20. So we're asking the question, what's the probability of being in this region? We don't say what's the probability of getting the result 3 out of 20. We say what's the probability of getting the result 0, 1, 2, or 3 out of 20. What's the probability of being in that region? So if our test statistic is 3, we're asking the question, is that probability of getting 0, 1, 2, or 3, is that 5% or lower? If that number is, if the probability of getting 0, 1, 2, or 3 is less than 5%, we have a significant result, okay? So let's crack on and have a look at one of the questions then. I've chosen question 5 for us to have a look at then. So in a manufacturing process, the proportion of faulty articles has found from long experience to be 0.1. So we'll start by assuming that the probability of finding a faulty article is still 0.1. That's our null hypothesis. We always assume that what they tell us in the question is true. What's always been true before is true. So that's how you spot your null hypothesis. It's found from a not long experience to be 0.1. So the probability of a faulty article is 0.1. Sample of 100 articles from a new manufacturing process is tested and 8 are found to be faulty. So our test statistic is 8. Now, you might want to just write that down somewhere. the test stat is 8, but we don't usually need to put that kind of as part of our formal answer. The manufacturers wish to test at the 5% level of significance whether or not there has been a reduction in the proportion of faulty articles. So that is that the alternative hypothesis is that the number of faulty articles is now smaller. Okay, so the probability of having a faulty article has gone down. That's what we're interested in. So if we were setting this out in an exam, we'd say let X be, I'm not going to bother writing this down, but let X be the number of faulty articles when we take a sample of 100 articles, okay? Then X, oh, by the way, that first line, very important, do write that down in the exam. Make sure the examiner knows what you're talking about. If you're going to introduce a capital X as a random variable, you've got to say how that capital X relates to what's going on in the question, okay? Then X is distributed with the binomial distribution 100, 0.1. Now that's what we think, okay? If the null hypothesis is correct, this is the situation we've got. And we start with that assumption. We start by assuming the null hypothesis is correct. What we've then got is we've got a test statistic of 8. So in this question, because it's the first one we've seen, they're splitting it down into 3 things. So the suitable test statistic is the number of faulty articles when we sampled 100 of them. The suitable hypothesis is this, H0 and H1. Explain the condition under which the null hypothesis is rejected. Well, what we're interested in is the probability of this random variable X not taking the value 8, but taking the value less than or equal to 8, because we're interested in, are we in the critical region, okay? Another way of thinking about the critical region is picture it like this. If this is 0 to 100, it would be possible to get no faulty articles if you took a sample of 100. It'd be possible to get 100 faulty articles. It tells us that the probability of a fault is 0.1, so you'd expect the peak to be somewhere around 10, wouldn't you? Okay, that's the if a tenth of these articles are faulty, then 10 out of 100 would be the number you get the most often. And then all the other numbers have got their own little probabilities. Picture it on one of these little charts, okay? What we're interested in is where's our critical region? Well, the critical region has to have a probability of 5% because we're at a 5% significance level. So let's say that if I take that probability, that probability, that probability, when I add those up, they make a total of 5%. The question is, where does 8 lie? Is 8 inside that critical region, or is 8 outside of that critical region? Okay, so we're not interested in just the probability of getting 8. We're not interested in just the height of 1 bar. We're interested in, oh, sorry, is that not visible? So there's a critical region. What's the probability of all of those things together? We're not interested in the height of 1 stick on its own. We're interested in, are we in this region or not, okay? Now, if we've got a 5% significance level, then those probabilities there are going to add up to 5%, or as close to 5% as we can get. We can't go over 5%, but as close as we can get to 5%. So we need to ask the question, what's the probability that this random variable X takes a value less than or equal to 8? Now, if we look at that, this is a question that we can answer now, okay? This is a random variable which is binomially distributed with 100 and 0.1. If we want to ask questions about random variables like this, if we want to ask this sort of question, then we can do that, because we either go to our calculator or we flip to the back of the book and we find the binomial distribution tables, the cumulative distribution tables. Now, the cumulative distribution tables in this book, only go up to n equals 50. So if we want to answer a question about an n equals 100 table, then we'd have to go to the calculator and look it up elsewhere. So I hope you'll indulge me. I'm just rather than stop and go and find my calculator or look it up on the internet. Let's just say let's take the two possible situations here. If the probability that this random variable is less than or equal to 8, we look it up, we find it from the calculator, and we find that we get a result of, I don't know, 0.04. So that's less than 5%. Then what we're saying is that we're in the critical region. The probability of getting 8 or less is smaller than the probability of getting 5% or less, so we're in the critical region. In which case we would say 3 things. We would say 0.04, and by the way, I'm just making this number up for the example. we'd say that that is less than 0.05 or 5%. So this is, I'm not going to write these down, but this is what you should write down. 3 things. This is a significant result. So we're in the critical region. Okay, so that is less than 5%. It is a significant result. We are in the critical region. That means we are going to reject H0. If it is a significant result, we reject H0. Now, I'm very careful always about not saying that we're going to accept H1. We're going to reject H0. We assume at the start of the question that H0 is true, therefore we can reject it. It's fair enough, I suppose, to say accept H1. What I would never do is say reject H1, because we've never assumed that H1 was true in the first place. Now, on the mark scheme, they are perfectly happy, apparently, with reject H1, even though we never assumed it was true. Personally, I'd say we reject H0, and I'd leave it at that. So we're rejecting H0, and then we need a comment in context. So we have significant evidence. So from the significance test, we have evidence to suggest that, and then we can quote straight from the question. There has been a reduction in the proportion of faulty articles. Okay, so that's the first option. If that number there is less than 5% or less than the significance level, we get that. Let's say it was not 0.04, let's say it was 0.06, then that's saying the probability being 8 or less is bigger than 5%. In other words, there's the 5% region, and 8 must be here because we have to add something else on to get up to this thing. In other words, the probability of this happening is not low enough, it's not unlikely enough to convince us that anything unusual has happened. We started by assuming that this was the case, the probability of a faulty article was 0.1. We still are quite happy with that. The thing that would convince us would be something unlikely. This is bigger than 5%, so it's not unlikely enough. So how do we draw the conclusion in a way that's going to get us the marks in the exam? Well, we say 0.06% or 6% is bigger than 0.05 or 5%. So this is not in the critical region, and it's not a significant result. Therefore, we accept H0. Therefore, there is not evidence to support the claim that, and then go back to the question. Okay? So 3 things to say. Tell me which way around the numbers are, and tell me, is it significant or is it not significant? Are we in the critical region or not? Then tell me, are we accepting or rejecting H0? And then put all of that into context. And that should get you the marks always on these questions. Now, there's a few fiddly things, and I'll deal with those in a separate video.